Hello students. So we are discussing Debye shielding, and we have realized that due to the presence of a test charge in the plasma, charge separation will be created, and as a result we will get to see an effective potential which we call as phi, and so del square phi is E times Ne minus Ni divided by epsilon naught. So, it is very important to understand the origin of this potential or the role of this potential in shielding the electric field, right. So, of course, there is a test charge, there is a potential, and there is an electric field. What is the potential? This potential has arisen because of the unequal number of electrons and ions in this cloud, right. So, within that cloud you have more electrons, right. So, this negative charge, most of the negative charge has given rise to this potential. Now, ideally if this potential is visible for the entire plasma, then there is no shielding, right. So, our expression that we are going to derive should be able to give us an inference that this potential will cease to exist after a point of time. After a certain distance, this will cease to exist. Only then we can establish the idea of shielding of the electric field by the plasma. So, whatever it is, so one thing is, as of now, even before we discuss the Debye's length or derive the Debye's length, so plasma is behaving collectively. So, all the plasma is behaving collectively to shield out the electric field, right. Now, let us take it ahead. So, we have to derive what is the form of phi. Okay. So, ideally we take the coordinates r, theta, phi, right. So, we need to have r, theta, phi. So, what does it mean? It means we have to find out how the potential will vary as a distance, as a function of distance away from the test charge, and how it vary in the angular direction and in the azimuthal direction, right. So, we have a 3-dimensional picture and we have something like this, right. So, we have to find out with respect to r, theta and phi. So, basically the Laplacian can be expanded in r, theta and phi, then we can use the right hand side, right. Now, at this point of time, what is the role of temperature? Because if there is no temperature, then the electrons movement will be restricted, right? They do not have any thermal motions, right, which means that given the temperatures, the number density of electrons will be something, it will follow some distributions, right. So, we can assume the Maxwellian distribution where the number n is n infinity exponential minus E by kBT. I think all of you are familiar with this distribution. This will just tell you at any given temperature how many number of electrons you can find with respect to the background number of electrons, right. So, you can use it to write the function fu, which is a exponential minus half mu square plus E phi divided by kBT. You see this is the kinetic energy. Electron has its kinetic energy by the virtue of its temperature, fine. Now, this additional energy E phi, when you are accelerating a charged particle with a potential V, the energy that it gains is EV. We know this, right. So, I have used the same E phi. I am calling the potential as phi instead of V, right. Now, there is a positive charge, just a quick recap. Now, there is a cloud of electrons around this positive charge. Within this cloud, the number of electrons is greater than number of ions, which creates a potential, and electron obviously sees this potential. So, electron sees this potential and gets an energy E phi. So, this is the full picture, right. These are the ingredients that we have in this particular recipe. So, if we want to understand what happens in totality, we should account each of these. We cannot neglect any of these and find out an expression, right. So, we can say that since the number of ions is constant, it is not moving, they are not moving. So, we say that number of ions is equal to number of an equilibrium number which is not changing, but the number of electrons on the other hand is n infinity e to the power of minus E, all of E plus by kBt. This is what we have, right. So, this E is kinetic energy plus E phi. Now, what we have to do is, let us say the kinetic energy is there, of course, when phi is 0, how will you find the number of electrons? Number of electrons, since we have written the distribution function, number of electrons can be minus infinity to infinity f of u du, right. So, at equilibrium, when phi is 0, we have the condition which is number of ions is equal to number of electrons. We are going to call this number as the n infinity, right. So, number of electrons as a function of r, let us say, will be n infinity exponential minus E phi by kBt, minus E by kBt. Okay. Here, let us say we don't talk about the background kinetic energy, we are rather more interested about the role or the influence of the potential phi. Okay. And okay. So, since charge is negative, we will write number of electrons as I am using E, the charge of electron, as minus E. So, I will write kBt. So, this is a very important relation. The meaning of this relation has a lot of significance in plasma physics. Okay. Now, let us use these things and try to derive an expression for the Debye's potential. Now, we have del square phi is equals to E times Ne minus Ni. So far, we are good, right. We accounted for the charge density first, then we accounted the electric field that can be produced out of that charge density. We wrote the electric field as the negative potential gradient. Now, we have a potential phi. See, the potential will tell you the expression for the potential, if it is written in all the coordinates, will tell you where is it strongest and where is it weakest. Okay. So, now we have to see how this del square phi can be expanded in the r theta phi coordinate system. So, del square phi, this is standard, you can refer to any book on simple vector calculus, you will find this expression readily available. So, del square phi is 1 by r square dou by dou r of r square dou phi by dou r plus 1 by r square sin theta dou by dou theta of sin theta dou phi by dou phi by dou theta plus 1 by r square sin square theta times dou square phi by dou phi square. This is the expression for del square phi. So, don't think how I got this expression. This is pretty standard, Laplacian in the spherical polar coordinate system. So, ideally, when Ni is equal to Ne, our potential simply becomes 0. This is the initial condition, right. We are deviating away from it, right. Let us assume the potential phi is symmetric in theta and phi directions. Theta and phi directions, it is symmetric. What does it mean? So, it is not varying with respect to theta and phi, that is it. So, it is only varying as a function of distance, but along the azimuth, it is not varying, it is constant, right. So, which means that we can neglect dou by dou theta terms and dou by dou small phi terms, they are 0. Since we are no longer dealing with 3 independent variables and 1 dependent variable, we have only 1 independent variable and 1 dependent variable. That means we can get rid of all the partial derivatives and we can write the total derivative, right. So, we will write. So, now all of this is del square phi. So, we have gotten rid of these terms. So, this is irrelevant, this is irrelevant and this one. So, we are only left with this. These are zeros, by the way, right. So, now we can write it as 1 by r square d by dr of r square d phi by dr is equal to E by epsilon naught. Yeah, we missed an epsilon naught when we got this expression. Del square phi is, yeah, I forgot to write an epsilon naught here. Sorry for that. So, this is E by epsilon naught. NE, we know NE is n infinity exponential E phi by kBt minus n infinity. You see, you have a positive term which appears in the exponential, which says that at higher energies you will have, that means you have more number of electrons at a given temperature. Generally, the distribution is opposite, right. But it is indeed true as long as you consider this plasma system within this cloud. Of course, this is valid, right. That is the beauty of this expression that you see here, right. Now, we can all this is not required. 1 by r square d by dr of r square d phi by dr is equals to E by epsilon naught n infinity exponential E phi by kt minus n infinity. Right. So, I will just rearrange the terms for convenience. So, some algebra which is essential for thorough understanding of the physics, d phi by dr is E n infinity by epsilon naught times exponential E phi by kBt. What is kB? kB is the Boltzmann's constant. Okay, fine. Now, let us say we impose a condition now that E phi is much less than kBt. Why do I need this condition? I want to write the first order approximation of this exponential. Then I have to have the condition that the power that appears in the exponential is small, so I can use it. So, I will write it again 1 by r square d by dr of r square d phi by dr is equal to E n infinity by epsilon naught times 1 plus E phi by kBt minus 1. I have written exponential as 1 plus x, because x square and all those terms will become very small as the numerator is very small in comparison to the denominator. So, only this term will also be very small, but we cannot just write it as 1, that is it, right. So, we have this because we need to have the variation. The exponential is representing something. So, maybe the smallest variation that it represents, we have to account for it. Okay, fine. So, here is the same thing, 1 by r square d by dr of r square d phi by dr is equals to E square n infinity phi by epsilon naught k b t. Right. The phi, the potential is a result of charge separation. The majority charges that are there inside this sphere or the electron cloud is obviously electrons, and the entire approximation is valid for electrons. So, it is appropriate to write the temperature as electron temperature. So, obviously, this is the electrons which are trying to see this potential and get accelerated or get some energy, right. So, now let us say we will make some substitution, right. So, we have a second order differential equation, right. So, phi is the independent variable here, and all of this obviously is a constant which is multiplying it. You see this? Isn't it? Let us say we call this constant. If you see what will be the dimension of this, okay, we can derive the dimension of this. You will realize that it will be something like 1 by length square. We just make some substitution, that is it. Lambda d square is epsilon naught k b t e divided by E square n infinity. So, what is lambda d? Lambda d is in the units of length. So, epsilon naught k b t e by E square n infinity is in the units of what do you say, square root of length. So, using this, I am just substituting this. Using this, we can write the equation as 1 by r square d by dr of r square d phi by dr is equals to phi lambda d raised to the power of minus 2. So, this is a differential equation, of course, and the solution of this differential equation. What is the solution of this differential equation? Solution is phi. We have still not obtained the form of the device potential. We only know if there is a radial variation in the device potential, what will it represent? That is what this equation is telling you, nothing more. Okay, we still have not derived what is the form for phi. How this potential has originated? This potential has originated by the introduction of a test charge, a positive test charge into the plasma, right. Let us say we take it ahead and let us see what we can do about it. So, this is still the same 1 by r square d by dr of r square d phi by dr is, I am going to call phi as phi of r. Why? Why? Because phi only varies as a function of r, but with respect to the other two coordinates, it is constant. I take this derivative inside, okay. I will keep 1 by r square outside. You have d by dr of uv. Taking the derivative inside, we have 2r d phi by dr plus r square d square phi by dr square, which is equals to phi of r divided by lambda d square. Taking the 1 by r square also inside, we have 2 by r d phi by dr plus d square phi by dr square is equals to phi of r divided by lambda d square, right. So, 2 by r d phi by dr plus d square phi by dr square is, so we will conveniently write it as d phi by dr plus d phi by dr plus r d square phi by dr square is equals to r phi of r divided by lambda d square. This is 2 d phi by dr, right? Once r is taken to the other side, 2 d phi by dr. So, we have written phi of r plus d phi by dr plus d phi by dr. So, these two we are going to write it as, it will remain d phi by dr, 1 d phi by dr will remain plus d by dr of r d phi by dr is equals to r phi of r by lambda d square. You understand? So, this is uv again. If I take this derivative inside, it will be, once it will be d square phi by dr square plus, you take the you keep it as v, then dr by dr is 1, right. So, this is still the same, just rewritten it. We can take d by dr as common and we will write d by dr of r phi is r phi of r by lambda d square. So, all of this is written like this. You just try to match, you will find out that both of them are same. Okay. You first take d by dr of this is uv, then you take a derivative on that, you will get back this. Maybe you can try it yourself and match both sides. Okay. Now, essentially all of this, now I can rewrite it as d square by dr square of r phi minus r phi of r by lambda d square is 0. You go back and see d square by dr square of r phi minus all of this is equals to 0, right. Let now at this point, let r phi is equals to x. We are changing the variables. Now, we can write our equation as, because we have r phi. So, if you see what I have done actually, I have just started from this equation, which is 1 by r square d by dr of r square d phi by dr is equals to phi times lambda d raised to the power of minus 2. So, instead of all this, I rearrange the terms so that this factor r times phi appears on both the sides of the equation. That is what I have right now. So, and then I am going to call r phi as x. In that case, I will write that equation as d square x by dr square. Now, here it is very important to note that x is not length. Okay. It is, of course, it is r times the potential. Potential, if you take q by 4 pi epsilon naught r, just the basic form. The actual form of potential is what actually we are trying to understand or we are trying to derive, but the dimension, the point is r phi is not distance, d square x by dr square minus x by lambda d square is equals to 0. Okay. So, this equation is okay for you to accept, right. It is not something very complicated. We followed all the first principles of derivatives or differentiation and arrived at this second order differential equation. Fine. Now, we have to solve it. Our job is still not done by deriving this equation, but let us try to understand the inference of this equation so that in the next lecture we can solve it and we can obtain the analytical form of phi of r. Where is this phi of r residing? It is residing inside this electron cloud. What about it? It is created because of this unequal number of charges inside this, or majority of electrons inside this and it so happens that this potential or the limit of this potential is only up to a particular distance, and beyond that distance this positive test charge or its presence cannot be felt. Okay, so we will conclude this lecture here, and in the next lecture we will try to solve this equation and obtain an analytical form for the Debye's potential, and also establish how the potential diminishes at the length, at the characteristic length, which we call as the Debye's length. Okay.